Endocrine system. The endocrine system is a system of glands, each of which is ductless and secretes the hormones into the bloodstream to regulate many functions of an organism, including growth, development, and metabolism. The blood and lymph carry hormones to the target organs. Hormones are substances, chemical mediators, released from endocrine tissue in the blood that attach to target cells and allow communication among cells. The ability of a target cell to respond to the hormone depends on the presence of receptors within the cell or on its plasma membrane to which the hormone can bind. On the basis of their chemical structure, hormones belong to four main types. Amino acid derivatives, for example, adrenaline, noradrenaline, and thyroxine. Small peptides, for example, enkephalin, vasopressin, and thyroid-releasing hormone. Proteins, for example, insulin, parahormone, and thyroid-stimulating hormone. Steroids, for example, progesterone, estrogens, testosterone, and cortisol. Classification of the endocrine structural components. Number 1. Central regulatory formations of the endocrine system: hypothalamus, hypophysis, cerebri, another term, pituitary gland. Pineal gland. Number 2. Peripheral endocrine organs: thyroid gland, parathyroid gland, adrenal, suprarenal glands. Number 3. Organs having endocrine and non-endocrine functions: primus, gonads, testes, ovaries, pancreas, placenta. Number 4. Isolated endocrine cells in the epithelium of the organs of the respiratory passages, gastrointestinal tract, urinary system. Apud cells, isolated endocrine cells which secrete steroid and other hormones. Apud cells situate a group of the endocrine cells which have the common function of the secreting low molecule weight polypeptide hormones. The name is derived from an abbreviation referring to the following: amine, for high amine content; precursor uptake, for high uptake of amine precursors; decarboxylase, for high content of the enzyme amino acid; decarboxylate, for conversion of precursors to amines. So, central endocrine organs: hypothalamus. The hypothalamus is a portion of the brain which is responsible for certain metabolic processes and other activities of the autonomic nervous system. It synthesizes and secretes certain neurohormones, often called hypothalamic releasing hormone, and this in turn stimulate or inhibit the secretion of pituitary hormones. The hypothalamus controls body temperature, hunger, thirst, fatigue, sleep, and circadian cycles. The hypothalamus contains neurosecretory magnocellular and paracellular nuclei. The secretory neurons of these nuclei have all characteristics of typical neurons, including the ability to produce the neurohormones. Neurosecretory nuclei of hypothalamus, depending on their sizes and functions, are subdivided into magnocellular and paracellular. Magnocellular nuclei, supraoptic and paraventricular. The axons of neurosecretory cells of these nuclei forming hypothalamo-hypophyseal tract pass along the infundibular stalk and terminate in neurohypophysis as accumulation is released to blood capillaries. These accumulations are called Heron's bodies. Neurosecretory cells of supraoptic nucleus secrete vasopressin, also called antidiuretic hormone, ADH. The main effect of vasopressin is to increase the permeability to water of the distal convoluted tubules and the collecting tubules of the kidney. As a result, water is absorbed by these tubules and urine becomes hypertonic. To contract smooth muscle tissue of small arteries and rises the blood pressure. The neurosecretory cell of paraventricular nucleus secrete oxytocin. Oxytocin stimulates contraction of the smooth muscle tissue of the uterine wall during childbirth, and myepithelial cells of alveoli of the mammary glands during the nursing. Paracellular nuclei. Neurosecretory cells of the paracellular nuclei synthesize and secrete certain neurohormones, often called hypothalamic releasing hormones, and this in turn stimulate or inhibit the secretion of the pituitary hormones, thyrotropic releasing hormone, gonadotropin releasing hormone, growth hormone releasing hormone. Pituitary gland. Since the pituitary gland developed from two separate embryonic origins, the epithelium of the pharyngeal roof and the floor of the diencephalon is frequently discussed as being subdividing into two parts. The adenohypophysis, pars anterior, pars tuberalis, and pars intermedia, and the neurohypophysis, pars nervosa, and infundibular stalk. The neurohypophysis is continuous with the median eminence of the hypothalamus via the thin urine infundibular stalk. It's through the infundibular stalk that axon to cell body located in the paraventricular and supraoptic neurons of the hypothalamus reach the terminal in the pars nervosa. The pituitary gland received its blood supply from the right and left superior hypophyseal arteries, serving the median eminence, pars tuberalis and infundibule, demonstrating that there is not only neural but also vascular connection between the median eminence and the pituitary gland. Additionally, branches from the right and left inferior hypophyseal arteries provide blood supply to the pars nervosa. The two superior hypophyseal arteries gives rise to a primary capillary plexus located in the region of the median eminence. These capillaries received releasing hormones produced by the neuron of the median eminence nucleus. Hypophyseal portal veins drain the primary capillaris plexus and deliver the blood containing these releasing hormones into the secondary capillary plexus. Both capillary plexuses are composed of fenestrated capillaries. The secondary capillary plexus is located in the pars arterium, where these releasing hormones control the activities of the parenchymal cells. It should be noted that blood also flows in the opening direction, that is, from the pituitary into the median eminence, thereby ensuring that communication occurs seamlessly in both directions. Moreover, the hypothalamus received information from the entire body as well as from other regions of the brain, permitting it perform its function in regulating homeostasis. Pars anterior. Pars distalis. The pars anterior pars distalis is composed of numerous parenchymal cells arranged in thick cords with large capillaries of the secondary capillary plexus, known as sinusoids, richly vascularizing the intervening regions. The parenchymal cells are classified into two main categories: those whose granules readily take up stain, chromophils, and those cells that don't possess a strong affinity to stain, chromophobes. Chromophils are of two types, acidophils and basophils. Hormones that modulate the secretory function of the pituitary-dependent endocrine glands are somatotropin, thyrotropin, follicle-stimulating hormone, luteinizing hormone, prolactin, adenocorticotropin, and melanocyte-stimulating hormone. It's believed that two types of acidophils produce somatotropin and prolactin, whereas various populations of basophils produce the remaining 5 hormones. Chromophobes, however, probably don't produce hormones. They are believed to be acidophils and basophils that have released their granules. An additional group of parenchymal cells are the non-secretory follicular stellate cells, whose function is not completely understood. The long processes these cells create gap junctions with each other, a characteristic that implies that they communicate with one another and perhaps aid in the regulation of chromophil function. It's also possible that they act as phagocytes or as regenerative cells to replace defunct acidophils and or basophils. Control of the arterial pituitary hormone release. The axon whose cell bodies are located in the paraventricular and arcuate nuclei of the hypothalamus terminate at the primary capillary bed. These axons store releasing hormones: somatotropin releasing hormone, prolactin releasing hormone, corticotropin releasing hormone, thyrotropin releasing hormone, luteinizing hormone releasing hormone, and inhibitory hormones, prolactin inhibiting hormone, inhibin, and somatostatin. The hormones are released by this axon into the primary capillary plexus and are conveyed to the secondary capillary plexus by the hypophyseal portal veins. The hormones then activate or inhibit the basophils and acidophils of pars anterior, causing them to release or prevent them from releasing their hormones. An additional control is the mechanism of negative feedback, so that the presence of specific plasma levels of the pituitary hormones prevents the chromophils from releasing additional quantities of their hormones. Pars intermediate forms a thin layer between the pars distalis and the narrow hypophysis. It contains small cells which produce melanocyte-stimulated hormone, MSH, which stimulates production of melanin by melanocytes, lipotropin or lipotropic hormone, LPH, which stimulates metabolism of fats. Pars tuberalis. The pars tuberalis form a partial coat around the infundible stalk. It may house basophils that may manufacture both luteinizing hormone and follicle-stimulated hormone. Pars nephrosa and infundibular stalk, the pars nervosa, doesn't present a very organized appearance. It's composed of pituitary cells believed to be neuroglial in nature and may fulfill a supporting function for the numerous unmyelinated axons of the pars nervosa. These axons, whose cells body are located in the supraoptic and paraventricular nuclei of the hypothalamus, enter the pars nervosa by the formation of the hypothalamo-hypophyseal tract. They possess expanded axon terminal referred to as herring bodies within the pars nervosa. Herring bodies contain oxytocin and antidiuretic hormone ADH, vasopressin, two neurosecretory hormones that are stored in the pars nervosa but are manufactured in the cell bodies in the hypothalamus. Oxytocin is a powerful smooth muscle constrictor that affects the muscular wall of the uterus during birth processes and also the myoepithelial cells of mammary glands to eject milk as the baby is feeding. Antidiuretic hormone prompts the cells of the kidney, collecting tubes to conserve water and then concentrate urine. The release of these neurosecretory hormones, neurosecretion, is mediated by nerve impulses and occurs at the interface between the axon terminals and the fenestrated capillaries. When the axon is ready to release its secreted product, the pituitary withdraw their processes and permit the secretory product a clear access to the capillaries. Pars tuberalis. The pars tuberalis is composed of numerous cuboid cells whose function is not known, but may house FSH and LH. In this picture, you can see pituitary gland and its hormone. Note, ACTH, TSH, FSH, LH, prolactin, growth hormone. This photomicrograph of the pituitary gland demonstrates the relationship of the gland of the hypothalamus, H, from which it's subtended by the infundibulum. The infundibulum is composed of an aeron portion of the infundibular stem and the surrounding pars tuberalis. Note that the third ventricle of the brain is continuous with the infundibular rhesus. The larger portion of the pituitary is the pars anterior, which is glandular and secretes numerous hormones. The neural component of the pituitary gland is the pars nervosa, PN, which doesn't manufacture its hormones but stores and releases them. Between the pars anterior and pars nervosa is the pars intermedia pale, which frequently presents at intraglandular cleft, a remnant of Ranke-Posch. The pars anterior is composed of large cords of cells that branch and anastomose with each other. These cords are surrounded by an extensive capillary network. However, these capillaries are wide, and the thalial line vessels known as sinusoids. The parenchymal cells of the anterior pituitary are divided into two groups, chromophils and chromophobes. It's somewhat difficult to discriminate between the acidophils and basophils of the pituitary gland stained with hypotoxylin and eosin. Even at high magnification, such as in this photomicrograph, only slight differences are noted. Acidophils stain pinkish and are slightly smaller in size than the basophils, which stain pale blue. In a black and white photomicrograph, basophils appear darker than acidophils. Chromophobes are readily recognizable since their cytoplasm is small and doesn't take up stain. The pars intermedia of the pituitary gland is situated between the pars anterior and the pars nervosa. It's characterized by basophils which are smaller than those of the pars anterior. Additionally, the pars intermedia contain colloid-filled follicles lined by pale, small, low cuboidal-shaped cells, roused. The pars nervosa of the pituitary gland is composed of elongated cell with long processes known as pituocytes, which are thought to be neuroglyph in nature. These cells, which possess more or less oval nuclei, appear to support numerous unmyelinated nerve fibers traveling from the hypothalamus via the hypothalamo-hypophyseal tract. These nerve fibers can be distinguished from the cytoplasm of pituocytes in a hematoxylin and eosin stained preparation. Neurosecretory materials pass along these nerve fibers and are stored in expanded regions at the termination of the fibers, which are then referred to as herring bodies, HB. Note that the pars nervosa resembles neural tissue. The boxed air is presented at a higher magnification. Next slide. This photomicrograph is a higher magnification of the boxed air of the figure 3. Note the numerous more or less oval nuclei, N, of the pituitary, some of whose processes arouse are clearly evident at this magnification. Then unmyelinated nerve fibers and processes of pituitary make up the cellular network of the pars nervosa, the expanded terminal regions of the nerve fibers which house neurosecretions are known as herring bodies. Also observe the presence of blood vessels, BV, in the pars nervosa. The pars anterior of the pituitary gland is derived from the epithelium of the pharyngeal roof and is composed of parenchymal cells arranged in thick cords. These cords of cells are surrounded by rich vascular tissue, BV, whose blood carries their secretion to their target cells. 3 types of parenchymal cells are visible with this stain: those whose granules stained red, known as acidophils A; those whose granules stained blue, known as basophils B; and those whose cytoplasm is limited and is devoid of granules, known as chromophobes C, because chromophobes have very little cytoplasm. The nuclei of the cells are very closely clustered, making them easy to recognize. The pars nervosa of the pituitary gland is derived from the hypothalamus and is composed of axons of neuron located in the paraventricular and paraoptic nuclei of the hypothalamus. The axons display expanded regions both along their length as well as at their termini, and these women, known as herring bodies, arouse house vasopressin or oxytocin depending on the origin of the axon. They release their hormone in the connective tissue surrounding blood vessels. Pituitary neurogland-like cells envelope these axons, providing physical and metabolic support. Pineal gland, epiphysis, cerebri, or pineal body. The pineal body is a small conical body, is evagination from the posterior part of the roof of the third ventricle of the brain. Connective tissue septa penetrate the pineal tissue and divide the organ into the irregular lobules. The parenchyma of the pineal lobule consists of 2 types of cell: pinealocytes, 90% of pineal cells, which have basophilic cytoplasm with large irregular lobate nuclei, long, highly branched processes with terminal buds that end in relation to the wall of the capillaries or in relation to the ependyma of the third ventricle. These cells produce melatonin and its precursor, serotonin. Interstitial pineal astrocytes. 5% of pineal cells are a specific type of neuroglial cells with elongated nuclei. These cells separate the pinealocytes from one another. Pineal gland may contain basophilic bodies, pineal sand, pineal contraction, consisting of concentric layers of calcium, magnesium, phosphate within an organic matrix. Appearance of contraction is a normal phenomenon which first registers in childhood With age, the amount and size is increased. The pineal gland is photosensitive and is important regulator of day-night cycle, circadian rhythms, and seasonal biorhythms. It obtains information about light and dark circles from retina via retinothalamic tract, which connect in the suprachiasmatic nucleus with sympathetic nervous tract traveling into pineal gland. During the day, light impulses inhibit the production of the major pineal gland hormone, melatonin. Plasma level of melatonin increasing during darkness and decreases during light. In humans, these circadian hinges of melatonin play an important role in the regulation of daily body rhythms. The pineal secretion promotes rhythms changes in the secretory activity of the gonads and other organs. Melatonin suppresses production of gonadotropin-releasing hormone by the hypothalamus, thus suppressing pituitary gonadotropin secretion and activation of gonadal growth and hormonal secretion. The pineal body is covered by a capsule of connective tissue derived from the pia mater. From this capsule, connective tissue trabecula enter the substance of the pineal body, subdividing into numerous incomplete lobules. Nerves and blood vessels travel in the trabecula to be distributed throughout the pineal, providing it with a rich vascular supply. In addition to endothelial and connective tissue cells, two other types of cells are present in the pineal, namely the parenchymal cells known as pinealocytes and neuroglian supporting cells. A characteristic feature of the pineal body is the deposit of calcified material known brain cell. The box there is presented at a high magnification in figure 4. This photomicrograph is a higher magnification of the box area of the figure 3. The larger, paler, more numerous nuclei belong to the pinealocytes. The smaller, denser nuclei are those of the neuroglial cells. The pale background is composed of the long intertwining processes of these two cell types. The center of the photomicrograph is occupied by brain sand, BS. Observe that this concretion increases in size by position of layers on the surfaces of the calcified material, as may be noted at the arrow. Note the two types of cells present in the pineal glands, the pinealocytes, whose nuclei are larger and lighter, staining than those of the neuroglia. Brain cell occupies some of the intercellular spaces of the pineal gland, you can see. Peripheral endocrine organs. Thyroid gland. The thyroid gland, enveloped by a connective tissue capsule, whose septa penetrate the substance of the gland, forming not only its supported framework but also a conduit for its rich vascular supply. The parenchymal cells of the gland are arranged in numerous follicles, composed of a simple cuboidal epithelium lining a central colloid filled lumen. The colloid is secreted and resorbed by the follicle cell and composed of the thyroid hormone that is bound to a large protein, and the complex is known as thyroglobulin. An additional secretory cell type, parafollicular cells, clear cells. These cells have no contact with the colloid material. They manufacture the hormone calcitonin, which is released directly into the connective tissue in the immediately vicinity of capillaries. Thyroid hormone is essential for regulating basal metabolism and for influencing growth rate and mental processes, and generally stimulates endocrine gland functioning. Calcitonin helps to decrease calcium concentration in the blood by inhibiting bone resorption by osteoclasts. When blood calcium levels are high, calcitonin is released. Follicular cells. The follicular cells vary in shape depending on the level of their activity. Normally, at an average level of activity, the cells are cuboidal, and the colloid in the follicle is moderate in amount. When inactive or resting, the cells are flat, squamous, and the follicle are distended with abundant colloid. Lastly, when the cells are highly active, they become columnar and colloids is scanted. Different follicles may show different levels of activity. Synthesis of the thyroid hormone. The synthesis of release of thyroid hormone takes place in two phases. In the first phase, thyroglobulin, a glycoprotein, is synthesized by granular endoplasmic reticulum and is packed into respectively secretory vacuoles in the Golgi complex. The vacuoles travel to the lumen surface where they release thyroglobulin into follicular cavity by exocytosis. Here, the thyroglobulin combine with iodine to form colloid. Colloid is iodinated thyroglobulin. In the second phase, particles of colloid are taken back into the cell by endocytosis. Within the cell, the iodinated thyroglobulin is acted upon by enzymes present in lysosomes, releasing hormones T3 and T4, which pass basally through the cells, though the cell and are released into blood. Hormone produced in the thyroglobulin gland is mainly T4, output of T3 being less than 10%. In the liver, in the kidneys, and some other tissue, T4 is converted to T3 by removal of one iodinized molecule. T3 and T4 circulating in blood are bound to a protein, thyroxine binding globulin. The bound form of hormone is not active. This photomicrograph presents part of lobe distaining many follicles F of various sizes. Each follicle is surrounded by slender connective tissue, CT, which support the follicle and brings blood vessels. In close approximation, the follicles are composed of follicular cells whose low cuboidal morphology indicates that the cells are not producing secretory product. During the active secretory cycle, these cells become taller in morphology, in addition to the follicular cells. Another parenchymal cell type is found in the thyroid gland. These cells don't border the colloid, are located on the periphery of the colloid follicles, and are known as parafollicular cells, or C cells. They are large and possess central places around nuclei, and their cytoplasm appears paler. The thyroid follicle F, presented in this photomicrograph, is surrounded by several other follicles and intervening connective tissue. The follicular cells are flattened, indicating that these cells are not actively secreting thyroglobulin. Note that the follicles are filled with the colloid material. Observe the presence of parafollicular cells, which may be distinguished from the surrounding cells by its pale cytoplasm arrow and larger nucleus. To the left picture, the low cuboidal follicular cells, FC, form the follicles that are filled with colloid. To the right, this is high magnification. The low cuboidal follicular cells are clearly evident, as are the parafollicular cells, whose clear cytoplasm is responsible for their additional name, that is, clear cells. Note also that the nuclei of the follicular cells are dark, whereas the nuclei of the parafollicular cells are stained much lighter. Parathyroid glands. The parathyroid glands are so called because they lie in the close relationship to the thyroid gland. Normally, there are two parathyroid glands, one superior and one inferior. On either side, there being 4 glands in all. Sometimes there may be as many as 8 parathyroids. Structure. Each gland has a connective tissue capsule, from which some septa extend into the gland substance. Within the gland, a network of reticular fibers supports the cells. Many fat cells are present in the stroma. The parenchyma of the gland is made up of cells that are arranged in cords. Numerous sinusoids lie in close relationship to the cells. Cells of paroid glands. The cells of paroid glands are 2 main types: chief cells, in other terms, principal cells; oxyphil cells, another name, eosinophil cells. First of all, chief cells. The chief cells are much more numerous than the oxyphil cells. With the light microscope, the chief cells are seen to be small round cells with vesicular nuclei. Their cytoplasm is clear and either mildly eosinophil or basophils. Sometimes the cells accumulate glycogen and lipids and looks clear. 3 types of chief cells: light, dark, and clear. have been described. With the EM active chief cells are seen to have abundant granular endoplasmic reticulum and well-developed Golgi complexes. Small secretory granules are seen especially in part of the cytoplasm near adjacent blood sinusoids. These features become much less prominent in inactive cells. Both active and inactive cells contain glycogen, the amount of which is greater in inactive cell. In the normal parathyroid, the human number of inactive cells is greater than that of active cells. The chief cells produce the parathyroid hormone, PARAT hormone. This hormone tends to increase the level of serum calcium by increasing bone resorption through stimulation of osteoclastic activity, increasing calcium resorption from renal tubules, and inhibiting phosphatase resorption, enhancing calcium absorption from the gut. Oxyphil cells. The oxyphil cells are much larger than the chief cells and contain granules that stain strongly with acid dyes. Their nuclei are smaller and stain more intensely than those of chief cells. They are less numerous than the chief cells. The oxyphil cells are absent in the young and a little before the age of puberty. With the EM, it's seen that granules of oxyphil cells are really mitochondria, large numbers of which are present in the cytoplasm. True secretory granules are not present. Note the functions of oxyphil cells are unknown. Although the parathyroid gland and thyroid glands are separated by their respective capsules, they are extremely close to each other. The capsule of the parathyroid gland sends trabecula of connective tissue carrying blood vessels into the substance of the gland. The parenchyma of the gland consists of two types of cells, namely chief cells, also known as principal cells, and oxyphil cells. Chief cells are more numerous and pores is darker, staining cytoplasm. Oxyphil cells stain lighter and are usually larger than chief cells, and their cells membranes are evident. A region similar to the box hair is presented in a higher magnification. This photomicrograph is a region similar to the boxed hair of figure 3. The chief cells of the parathyroid gland form small cords surrounded by slender connective tissue elements and blood vessels. The nuclei of the connective tissue cells may be easily recognized due to the elongated appearance. Oxyphil cells possess a pale cytoplasm, and frequently their cell membranes are evident arose. The glands of older individuals may become infiltrated by adipocytes or fat cells. Note that the smaller chief cells are crowded together, whereas the oxyphil cells that are equally as crowded together appear to be more loosely arranged due to their larger cytoplasm. Suprarenal glands. The suprarenal glands, adrenal glands, another term in some animals, are invested by a connective tissue capsule. The glands are derived from two different embryonic origins, named mesodermal epithelium, which gives rise to the cortex, and the neuroectoderm, from which the medulla originates. The rich vascular supply of the gland is conveyed to the interior in connective tissue elements derived from the capsule. Cortex. The cortex is subdivided in three concentric regions or zones that secrete specific hormones. Control of these hormonal secretions is mostly regulated by ACTH from the pituitary gland, as you know. The outmost region just beneath the capsule is the zona glomerulosa, where the cells are arranged in arches and spherical clusters with numerous capillaries surrounding them. Cells of the zona glomerulosa secrete aldosterone, a mineralocorticoid that acts on cells of the distal convoluted tubules of the kidney to modulate water and electrolyte balance, as you know. The second region, the zona fasciculator, is the most extensive. Its parenchymal cells, usually known as spongiocytes, are arranged in long cords with numerous capillaries between the cords. Zona fasciculator cells secrete cortisol and corticosterone. These glucocorticoids regulate carbohydrate metabolism, facilitate the catabolism of fats and proteins, exhibit anti-inflammatory activity, they suppress the immune response. The innermost region of the cortex, the zona reticularis, is arranged in anastomosing cords of cells which reach intervening capillary network. Zona reticularis cells secrete weak androgens that promote masculine characteristics. At the junction of the zona fasciculator with the zona glomerulosa, there are regenerative cells known as progenitor cells that can enter the cell cycle to form new cells to replace defunct parenchymal cells of the suprarenal cortex. Medulla. Parenchymal cells of the medulla derived from neural crest material are disposed in irregular arranged short cords surrounded by capillary networks. They contain numerous glandules that stain intensively when they're fresh, and the cells are called chromaffin cells. These are two populations of chromaffin cells that secrete the two hormones of the suprarenal medulla mainly, epinephrine, adrenaline, or norepinephrine, noradrenal. Secretion of these two catecholamines is directly regulated by preganglionic fibers of the sympathetic nervous system that impinge of the postganglionic sympathetic neuron-like chromaffin cells, which are considered to be related to postganglionic sympathetic neurons. Catecholamine release occurs in physical and psychological stress. Moreover, scattered large ganglionic sympathetic ganglion cells in the medulla act on smooth muscle cells of the medullary veins, thus controlling blood flow in the cortex. The suprarenal gland, usually embedded in adipocytes tissue, is invested by a collagenous connective tissue capsule that provides thin connective tissue elements that carry blood vessels and nerves into the substance of the gland. The cortex is divided into 3 concentric regions: the outermost zone, glomerulosa, middle zone, fasciculator, and the innermost zona reticularis. The medulla, which is always bounded by zona reticularis, possesses several large veins, which are always accompanied by a considerable amount of connective tissue. The collagenous connective tissue capsule of the suprarenal gland is surrounded by adipose tissue through which blood vessels and nerve reach the gland. The parenchymal cells of the cortex immediately deep to the capsule are arranged in an irregular array, forming the more or less oval to round clusters or arch-like cords of the zona glomerulosa. The cells of zona fasciculator form long, straight columns of cords orientated radially, each being 1 or 2 cells in width. These cells are larger than those of zona glomerulosa. They present a vaticulated appearance due to the numerous lipid droplets. They were extended during processing and are often referred to as spongiocytes. The interstitial is richly vacuolized by blood vessels. The columnar arrangement of the cords of zona fasciculata is readily evident by viewing the architecture of the blood vessels indicated by the arrows. The cells in the deeper region of zona fasciculata are smaller and appear denser than the more superficial located spongiocytes. Cells of the zona reticularis are arranged in irregular anastomosing cords. Those intestines contain wide capillaries. The cords of the zona reticularis merge almost imperceptibly with those of zona fasciculata. This is a relatively narrow region of the cortex. The medulla is clearly evident since its cells are much larger than those of zona reticularis. Moreover, numerous large veins are characteristic of the medulla. The capsule of the suprarenal glands displays its collagen fibers and the nuclei of the fibroblasts. The zona glomerulosa, which occupied the upper part of the photomicrograph, displays relatively small cells with few vacuoles arrows. The lower part of the photomicrograph demonstrates the zona fasciculata, whose cells are larger and display more vacuolated arrowheads appearance. Note the presence of connective tissue elements and blood vessels between cords and parenchymal cells. The cells of adrenal medulla, often referred to chromatin cells, are arranged in round to the ovoid clusters or in irregularly arranged short cords. The cells are larger and more or less rounded to polyhedral in shape with a pale cytoplasm and vesicular appearing nucleus displaying a single large nucleolus. The interstitium present large veins and an extremely capillary network. Large ganglion cells are occasionally noted. Thank you.